Good evening or good morning, everyone. Now that you've watched the first two videos that we have posted on our Algebra 2 virtual learning webpage about getting an idea what exponential functions graphs look like, both growing ones and decaying ones, I just kind of want to walk through a Desmos demonstration of this stuff with the H decay and the A and what it does to the graph. And then I'm also going to walk through an example from beginning to end, just kind of showing you how the parent function transforms into the given function using our transforming technique that we've done over the course of the year so far. So a lot of this stuff you're going to see is correlating the same. And then with that, you guys are able to come into office hours, ask questions, and then reiterate or re-go through the video to make sure you understand everything that's going on. So I'm just going to kind of walk through 4 or 5 slides here. I'll point some key things out, and then I'm going to jump over to Desmos as well to show you. So to start things off from that video, you should realize that if the B value is greater than 1, then we know we have a growth, which means that graph is rapidly increasing as we go from left to right, but it's never going to cross the x-axis. Where if the B value is greater than 0 but less than 1, so basically a fraction, it's going to be decaying, so it's going to be decreasing from left to right on the graph, approaching the x-axis. So and we get to the Desmos thing, I'll show you a little bit of difference between it. So the B value is what's really going to distinguish how these graphs look and what the shape they're doing and the creation that they have, which is why the range value is going to be kind of restricted a little bit more than what we've done in the past. In the past, we've been restricting the domain. With exponential functions, the domain will always be all real numbers. We're always going to be able to plug a value in to our exponentials and be able to get a value out. It's just that now we're going to change the look of what the range values look like. So a couple things looking at the table, that's probably the most important part, is that negative x values, and then when you have a negative exponent, it's just a reciprocal. So when I go b to the negative third or 2 to the negative third, it becomes 1 over 8, so 1/8. So it turns into a fraction. So it's going to get really, really small as you go negative. But then is 0, 1, the one that will never change is that anything to the 0 power is always going to have a 1 out. So this is kind of going to be our starting point. We're going to see that the starting point is always going to be 1 unit away from your horizontal asymptote when there's no dilation factor at all. So when there's no a value in front of this, then this starting point will always be 1 unit on the y-axis away from the x-axis. So we'll always be going up. And then it's just b squared, bq. So there's going to always be a pattern to it. So with that said, you're going to be able to click, I'm going to click on the Desmos link, which is going to kick us here. I kind of want to just show what's going on with the graph, how things are moving, how things are shifting. Currently, both these graphs are on top of each other. So I have y equals 2 to the x is called the parent function. And then the second one is going to be me moving things. So right now, as I move the b value, as I change the base, we notice that the bigger the base gets, the faster the graph kind of increases. So if I change this all the way to 4.1, or we'll go to 5 here, looking at the distances is that when I go 1 unit to the right, I'm now going up 5 units. Where on the parent function, I went 1 unit to the right, I only went up 2, as you can see here. So the difference is that the b value distinguishes how fast you are increasing, in this case, when the b value is greater than 1. But if I go down to where the b value is less than 1, so if I go 0.7, we'll go 0.5, you kind of see the correspondence here, is that now instead of this being over 1 up 1 with the parent function of when it's y equals 2 to the x, now it's going to be over 1 up a half. So that b value is always going to be your shift that you're going to go up from the horizontal unit. So as I move right 1, right 1, I go up a half. Or if I go left 1, so I'm going backwards now, which I'm thinking a negative exponent, I'm actually going to go up 2. So these graphs are kind of like flipped from each other, because the red graph is a growth, and with this new b value being a half, it now becomes a decay. So the graph is falling from left to right as it approaches the asymptote of x equals or y equals 0, where the growth red graph is increasing at a rapid rate of 2 times per x value, with an asymptote of still the x-intercept is just never going to cross as we get closer and closer to 0. So the b value is going to kind of really distinguish the shape of our overall graph as we look at this as it moves. And notice that point is just moving, but the one point that never changes is my starting point, is 0, 1 right now. And notice that it's still 1 unit away from my horizontal asymptote, which is the x-axis. And then now you might ask, if I change this to be -3, and I do the same thing, now it's being flipped. And then the only other thing that we have to worry about with the b value is that the b value can never be negative, because we can't take, if I go -1 here and I hit play and I go to a negative, you're inputting a -1 to the x power. Well, there's no such thing as -1 to the x power. It's saying -1 times 1 to the x power. So we don't have any negative bases. Your bases will always have to remain positive. That way we know it's an exponential growth or an exponential decay that point is moving along. So let's move the base back to 2. And now we're going to look at what h and k do. So a little bit of review of what h and k. H is going to be our horizontal movement. So as we move left and right, all I'm doing is I'm shifting the base points from the parent function. So 0, 1, and 1, 2 are now moving 2 units to the right, so they become 3, 2, 2, 1. So the y values stay the same. I'm only adding the x values to it. So my ordered pair here of 1, 2 now becomes 3, 2 because I added 2 to 1. My ordered pair that was 0, 1 became 2, 1 because I added 2 to the 0. So the h value is going to be your horizontal movement with the function, where the k value is going to be your up and down. So as k increases, the graph is just picking up. So notice 0, 1 became 0, 4, 1, 2 became 1, 5. So my x inputs did not change, my y values have changed, which makes us note that our asymptote now for the parent function was now the x-axis, but our asymptote for this one is going to be, this graph gets closer and closer to the value of 3. So my k value has created my horizontal asymptote. So a little review here. H going left and right. K is going up and down. And that will work for whatever function that we have. So if I change the base to be, let's say we want it to be 4. And then I'm going to toggle out the parent function. So for 2x, parent function for 4x. So now what it's doing is it's taking those base points from the parent function and I'm moving it, in this case, I'm moving it horizontal from 1, 4, now it became 3, 6 because I went right 2, up 2. Every point went right 2, up 2. Every point went right 2, up 2. So it's creating this transformation and the base value does not change. The only thing that changed is my horizontal asymptote has changed because I'm adding or subtracting a k value to it. So let's get the k value back down to 0 and the h value back down to 0. And we'll go base back down to 2 just so we can compare, keep the graphs pretty simple for right now. So the one thing we got left to do is just talking about the a value. So the a value has been always a trickier one. It's the dilation value. So if I move this to, let's say 3, let's just notice the difference between the ordered pairs. We started with 0, 1, 1, 2, as my parent function. But then when you add a dilation value or an a value of 3, now it becomes 0, 3, 1, 2, becomes 1, 6. And then this ordered pair here that was at 2, 4 would now become 2, let me zoom out here a little bit, would become 2, 12. So when we look at the dilation, I like to look at the distance from the horizontal asymptote. Here, this distance is 1. And now if I add a dilation value of 3, now this distance is 3 units. So it's 3 times bigger distance away from the horizontal asymptote. And that's every point. So the distance that was here was 2 because the base was 2. Now it's going to be 6 times. So that dilation factor just increases the y value of the parent function. So whatever that parent function is, if that parent function is 1, 2, 1 unit to the right, 2 units up, and you have a dilation factor of 3, now it's going to become 1 to the right, 6 units up. Where if I change this value to 4, then it's going to be 1 to the right, 8 values up. So it's going to take the b value, the base, and multiply it by the 4 value. So you're multiplying the y value. You're going to multiply the y value of the parent function when you're changing it. So this is why the parent functions are so important. Knowing the parent function from the original, whether it's 2 to the x, 3 to the x, or 4 to the x. Same thing if it's down here, your parent functions are a half, 1/3, 1/4. All they are is the difference in directions that you are traveling. So when we look at putting all these together, when we look over here, kind of reiterate a couple things here before the time runs up, is the a is the dilation value, so it's affecting the y value. And if it's negative, let's go back to here. If I make the dilation, let's say -3, instead of going, I should just make it -1 first. Instead of going 0, +1, we would now go 0, -1. Instead of going to the right 1, up 2, we now go to the right 1, down 2. So the negative just does a reflection over the x-axis, and then you take the absolute value of that a value to figure out how far away I am from the horizontal asymptote. So I'm 3 units away from the horizontal asymptote here. I'm 6 units away from the horizontal asymptote here because I tripled this distance away. So the b is your base. If it's greater than 1, it's a growth. If it's between 0 and 1, it's a decay. And then we can't have any negatives because we can't take a negative base to a power. H and K is just like we did with quadratics. H is your horizontal movement. K is your vertical movement. So therefore, H changes the x value of the parent function, or Y changes or the K changes the y value of the parent function. The big huge key is that without having to graph, you should be able to find your horizontal asymptote by looking at, am I adding or subtracting to the parent function? If you are adding or subtracting to the parent function, your horizontal asymptote will be that K value, or the value that you are adding or subtracting the parent function to. So in terms of the process of graphing these, you should always do your dilation value first, and then do your left and right movement when you're graphing these. And that will come up on the next part 2 of this video due to time constraints with my software. So, and in my next video, we'll finish up these 2 examples, and we'll go from there. All right, and then again, if you guys got any questions, please feel free to email me, Mr. Geiger, Mrs. Flores with your questions, or just pop in on office hours for your designated class. So, thank you.